Okay, so today we're going to review chapter 17 on this. Another word for all those of that whole list is chemical thermodynamics. And that's for exam 6. That will be next Monday. Today we're going to finish up a review on this and then go in the lab and have some fun. All right, I'm going to work from version 2 of the review document. Unfortunately, I didn't get a chance to highlight them like I usually do, so I'm gonna have to work from my hard copy and go back and forth. But hopefully it won't be something that you'll notice. All right, so the first one I've got marked off as number 2. Let's see. Get that out of the way. Oops. Nope, it's not behaving. Let's try this. Let's disconnect and reconnect. Okay, cursor's moving. Yeah, there's the cursor. And nope, might as well leave that alone for now. Seems like the video card's not the only thing going bad. So let's scroll down to number 2. And let's see, I'm going to have to do this so I can see things. There we go. Number 2. All right. This problem addresses probability. How do you determine probability? If you've never had statistics, and this will be new to you. But hopefully in basic math, they might have touched on it a little bit. Anyway, let's say we have a 2-bulb flask containing 5 particles. Yeah, 2-bulb flask. Containing 5 particles, A and B and C and D and E. Okay. Right now, they're all in one side. What's the probability of finding all 5 particles on the left side where they are? Probability is the number of possibilities out of the total possibilities. So we need to know the total possibilities in order to determine that. Let's see if there's an easier way. It might get us through this quicker. Yeah, there is an easier way. What's the probability of finding 1 particle on the left and not the right? Well, there are 2 choices. 1, 1, 2. So that probability for A would be 1/2 or 50%. If we incorporate B, then we have A on this side, B on that side, or A on this side, B on this side, or A on that side, B on that side, or the other way around. So actually you have 1 in 4, which is squared. Okay, do the same thing for the 3rd one, and for the 4th one, and for the 5th one. 1, 2, 3, 4, 5. So actually that's 2 to the 5th power is what we're looking at. 1 divided by 2 to the 5th. Thank you. Stop me if this is stretching your imagination. Okay. So what's 2 to the 5th? Well, let's see. 2 times squared is 4, 8, 16, 32, right? 1/32. But the answer is given in percent. Right. So we just have to convert that to percent. And I'll take the inverse, and times 100 is 3 point. Let's see. How many significant figures we need? 3.13%. would be the probability in terms of percent. It's either 1 in 32 or 3.13%, which would be 3.13 times in 100. Okay. All right, that was number 2. It's pretty good. Must have used a polish on it. Let's see. Let's skip down to number 14. Go. The process of CHCl3, which is trichloromethane. CHCl3. What is that? That's a solid to a liquid. Okay, so we're going from a solid to a liquid. Okay. What else are we told? The delta H is 9.19 kilojoules per mole. Kilojoules per mole. And the enthalpy is 43.9 joules per mole K. Short-term memory loss. 43 joules per mole K. Okay, that's given. What's the melting point of chloroform? Right. Yeah, that's another name for it. Chloroform, trichloromethane. It's the same thing. So what's happening at the melting point? We're at an equilibrium, right? If you've got some of this and some of that, then you're at a situation of equilibrium. So I'm going to refresh my memory. All right. So remember we determined that for surroundings is equal to negative delta H over T. Well, if you're at equilibrium, then both the delta S total being equal to delta S system plus delta S surroundings. If it's at equilibrium, then the delta S is 0. Right? So that means delta S for the system is just change of sign. Like that. Okay. And this is the melting point. So we have both values. We have this one and that one. And then under standard conditions. So all we have to do is substitute in these values. System would be 43.9 joules per mole K equals delta H. But these are in different units, see? Kilojoules and joules. So we need this one to be in joules. 19 times 10 to the third joules. I just took that K and turned it into 10 to the third per mole divided by the temperature. So now we can solve for the temperature. And this is going to be in Kelvin, right? Because of that factor right there. So we bring T over here, put that one over there. In fact, it's 9.19 times 10 to the third divided by 43.9, which is 209.3 K. Now, is it in K or no, it's in degrees C. Okay. So we have to subtract 273, which is minus 64 degrees C. That would be the melting point of chloroform. Okay. All right. Yeah, the only time that delta S surroundings and delta S system are equal in magnitude but opposite in sign is at the phase change. All right, let's see. That was 14. Let's try 20. Here we go. In which case must a reaction be spontaneous at all temperatures? Okay. If we're looking at spontaneous, we're comparing. The best way to approach this is to use a formula that has temperature in its makeup, and that's Gibbs free energy. It's delta H minus T delta S. So we have a temperature factor in here. That's important for answering this question. So in order for this to be spontaneous, what does delta G have to be? Right, what sign is it? It has to be negative. This must be negative for the process to be spontaneous. So how do you get negative out of this? Well, you could have this negative and you can have that positive. Because of that negative sign, then it doesn't matter what the temperature is. This is always going to be negative, and that's always going to be negative. So under those conditions, yeah, all temperatures is going to be spontaneous. If delta H is, if it's exothermic and the entropy is positive. So let's see, that would be D. Okay. I'm probably not telling you something you didn't already know, right? That's a good sign. Okay, 26. Okay, when a stable diatomic molecule, 26. When a stable diatomic molecule spontaneously forms from its atoms. All right, I got it backwards. Spontaneously forms from its atoms. These are both gas, and the diatomic molecule. There we go. Okay, why does it have to be gas? You remember? Because we don't want any other processes interfering with what we learned from this process. In other words, if these are liquid, then you got to turn them into gas before you get there. Or if they're all liquids, then you got to go gas and then back to liquid, and you're introducing other factors that muddy the water. So we want gas, gas, gas. Okay, spontaneously forms from its atoms. When it's spontaneous, that means that delta S total is positive. It has to be. And delta G has to be negative. Okay. All right. What are the signs of standard? All right, delta H, 0, delta S next, and delta G. All right. We know that this one, since it's spontaneous, this one has to be negative. And these are under standard conditions. All right. What do we know about this one? Well, when you bring two atoms together and they form a bond, they give up energy. Because they only bond because it's at a more stable situation. And that means you give up some energy. Lower energy means more stable. So this is exothermic. That makes this one negative. Okay, I think that's the tricky one right there. So what do we know? Delta G equals delta H minus T delta S. So if this one's negative, this one's negative, then this one, let's see, positive would be the best. If this were negative, then T would have to be very small T. Is that one of our options, or is it just asking for the best answer? Just asking for the best answer. Okay. Spontaneous from what are the signs of each one? Oh, hold on a second. Because it's saying oh, okay. Okay. I got it. Excuse me, brain farts. Let's look at this in terms of, we're answering this question. Let's look at this in terms of randomness, right? This is less random than this. Right? These are separate atoms. This is one. So you're going from 2 moles down to 1. That means this has to be negative. Okay. So all of them are negative. And the only way that this one can be negative is if this one is very small. So very low temperature is where that happens. Now that's not part of the problem, but it's nonetheless, it's true. Okay. Did I lose anybody? Okay. All right, let's see, 26, let's go to 31. Here we go. Yeah, 31. All right, calculate the KSP, solubility product for the salt sodium chloride at 25 degrees. So we're looking for the KSP for sodium chloride at standard temperature. Okay, and we're given this information, our delta G's of formation. So rather than write those up there, I'll just refer to them as we go. You have to do 2 things here. Work backwards. So how is KSP related to the spontaneity of this reaction? Delta G0 equals I got to refresh my memory. Yeah, minus RT log K. So this will give us the KSP. What we need to do is find out what this one is. Delta G0. And since this is an equilibrium process where we have well, obviously it's equilibrium, but we can use this one because we know that delta G is 0. That's why delta G0 can be equal to these. Remember, delta G is equal to delta G0 plus RT log Q. And if we're at equilibrium, that means this one's 0. So then you can solve for that one. And that's where this expression comes from. Well, we need to find out what delta G0 is. Delta G0 is equal to the sum. It's the sum of the products minus reactants. Delta G0 is for the products minus the delta G0s for the reactants. So we can do that. Now all we have to do is say, all right, what are the products? Well, if it's solubility product, then we say sodium chloride is going to sodium ion and chloride ion. Okay, so the product, we need the delta G for the sodium ion is minus 262. And this is in kilojoules per mole. And then we have chloride, which is minus 131. And then we subtract reactants. Sodium chloride, I should put a solid here, because that's what it is before it goes into solution. Minus 383.8. Minus 380. Okay, so that's going to be a positive. These are both going to be negatives. And I'm going to use my calculator because my brain's not working all day. 383.8 and then 262, subtract that one, and 131, subtract that one. And we didn't have to multiply by any coefficients because they're all 1, 1, 1. So delta G0 is going to be minus 9.2 kilojoules per mole. Let's see if I did that right. I want to check it. Yeah. Okay. And this value right here is 8.3145, I believe, joules per k-mole. So delta G0, actually we're using this one, minus 9.2 kilojoules would be times 10 to the third joules per mole. And then our R value, or minus our R value, 8.3145 joules per k-mole. And then temperature is 25 plus 273. So that has to be in K. And then we say log of KSP and solve for KSP. And so let's see, I can divide this one by that one because they're all multiplies. 8.3145. And then 25 plus 273 is 298. 298, divide that in there. So the log of KSP is equal to 3.713 times 10 to the minus 3. And how do we get KSP out of this? E to that power is equal to this. Right? It's the anti-log. So let's see. If the number's already in there, I just need to find my e to the x. Here it is. E to the x. Here we go. So this is 1.004. I did that right. No, I must not have. What did I do wrong? All right. Let's see if I got all these values in here right. Products. Minus 262. Yes. Minus 131. Minus 383.8. So 383.8 liters. And 262 minus 1 minus is minus 9.2. That makes this delta G0 minus 9.2 times 10 to the third joules per mole. This one is 8.3145. That's right. This one is temperature is 25 to 98. That's right. Okay. So let me check my math on this one, and I think I know what I did wrong. I left it in my calculator as kilojoules. So I need to multiply this times 1,000 and then divide by 8.3145. Okay. And then divide by 298. Okay. Now I've got 3.713. And KSP is e to that power, which is 41. Okay. All right. Was 31. Let's see, 34. All right. This one's simpler than it looks. 34. Bring this with me. Consider the gas phase reaction where we have NO gas plus 1/2 O2 S yields NO2 gas. Okay. That looks like the type of format that we use for heat of formation for this one. And the delta H for that one, delta H0 is minus 56.91 kilojoules. And K equals 1.46 times 10 to the 6th at 25 degrees C. Okay, that's everything we're given. Question about this system is, at equilibrium, how will raising the temperature affect the amount of NO present? Okay, that's why I said it was really simple. If we invoke Le Chatelier's principle, we treat the heat as a component in the reaction mechanism. So if this is negative, that means it's exothermic, right? So which side does the exothermic heat go on? That side. So this would be plus delta H on this side. Now, raising the temperature adds heat to this side and drives the reaction back. So this one will increase. Yep, that's it. A lot of blue smoke here. All you need is the reaction and delta H. K doesn't matter. Now, of course, this K does tell us that the products are highly favored, which probably means that the delta G is extremely negative, or the delta H, the delta S total is very high, a lot positive. But that wasn't part of the problem. It was just a little bit of extra information. Okay, 34, 40. All right. Scroll to 40. Scroll to 40. Here we go. With me. Okay, the second law of thermodynamics. Oh. All right, so the second law. What is the second? States that. Well, let's see. All right. E says none of these are correct, so we have to look at each one. Energy is conserved in a spontaneous process. What's A? Energy is conserved. Energy is always conserved, which is the first law. Right? Delta E for the universe is equal to 0. That's the first law. B, entropy of the universe increases during a spontaneous process. That's one way of saying it, right? Delta S for the universe is always greater than 0. Yeah, that's a good one. So it can't be E. The heat content of the universe increases during a spontaneous. No, this would be contradictory to that one. Right, so that one can't be it. And D, all of these are valid components of the second law. No, just this one. So that's the best answer. Delta S for the universe is always increasing. And I threw in that during a spontaneous process. I guess that's given, right? In other words, if the process is spontaneous, it's not going to go for the whole universe is concerned. Right? Maybe on a local level, you can get a non-spontaneous process to go, but it has to be coupled to a spontaneous process to drive it. Right. So that's a valid statement. All right. How about 42? Hope I don't have to do that much work. Let's see what 42 is anyway. And scroll. Here we go. Yeah, squeeze it in. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light. So we've got hydrogen gas, diatomic, plus chlorine gas, diatomic, and it remains unreacted until exposed. Oh, and then they give us the reaction. 2HCl gas, hydrogen chloride. Right? Then the reaction occurs very rapidly. So what does that mean? Exposing it to ultraviolet light. That means the light provided the activation energy. Remember this diagram? It's probably like this. This is activation energy. And in our case, that's provided by ultraviolet light. Otherwise, it just sit there. What else are we given? We're given delta G, delta H, and delta S for the reaction. Which of the following is consistent with this information? All right. How about A? The reactants are thermodynamically more stable than the products. Thermodynamically. If the reactants are thermodynamically more stable than the products, then that just means that they want to stay on this side. That seems reasonable. Is A reasonable? Oh, okay. So we're going to have to look at the values. All right, so let's put those up here. I see what they're saying. Work from the numbers. And delta S is 4.76 joules per K. Okay, if we take the numbers and not try to reason it out, but actually go with the evidence, thermodynamic stability says that the delta G would be positive. It would not be a spontaneous process. In this case, delta G is negative, so this one would be false because the products are more stable. Okay. How about the second one? The reaction has a small equilibrium constant. Small KEQ. Well, how would we do that? We could use the formula. Yeah, we could use the formula. Delta G0 equals minus RT log K. So this would be a minus 45.54. This should be times 10 to the third, because this one has 3.145. This one has joules rather than kilojoules. Yeah. And then the temperature, under standard conditions, so it'd be 298 at 25 degrees C, and then log K. So let's see. What's K? I think I can do it right this time. Let's see, 45.54, change the sign, exponent 3, and then 8.3145, change that sign, divide, and then divide by 298. So log K is 1.8. Take that out, call it this 18.38. So K is e to that power 9.6 times 10 to the 7th. That doesn't look small to me. That looks large. So that statement is false. See, this one is that's the correct statement. The one given to us was false there. Okay, how about C? C. The ultraviolet light raises the temperature of the system and makes the reaction more favorable. Well, no, it doesn't raise the temperature. All it does is provide activation energy. Now, one way to provide the activation energy is to raise the temperature, right? That would be one way. But in this way, we just provided enough energy for the molecules to get over the hump. So we didn't necessarily raise the temperature. So we can't say that that's true, not with the information that's given. D, the negative value for delta S slows down the reaction. All right. This is kind of a trick question. If delta S equals a negative value, says anything about the kinetics, it's news to me. This is equilibrium. The rate of the reaction has nothing to do with these values. And it looks like by process of elimination, we're down to E. The reaction is spontaneous, but the reactants are kinetically stable. All right. Spontaneous, yes. Because delta G is negative. But kinetically stable. Okay. The only way that I can reason kinetic stability is the fact that it's sitting there. And over the short term, the reaction doesn't go until we influence that activation energy. Remember, this is the region of this plot that speaks to kinetics. And this region is equilibrium or thermodynamics. Okay. So I'm going to say that it's kinetically stable because it needs energy to get over that hump. And we can only provide it either with heat or with ultraviolet light. Right. So that's the reasoning behind this one, claiming that this one is true. It's spontaneous, but kinetically stable. And we didn't derive kinetic stability from any of these terms over here because they don't speak to kinetics. Only the activation energy from UV talks about kinetics. That's why we can say it's kinetically stable. I think that's why I put that one in there, because that could be confusing. Okay. 52. Yeah. 52. We're not finished. We're not finished early. Then we have to wait around for the rest of the class to show up before we can do the lab, right? Two. All right. So we have the equilibrium constant of a certain reaction was measured at various temperatures to give the plot shown below. So we got this plot. Let me see if I can rough it out, just so I can talk about it. And we're going from, actually they've got the natural log of K, and they're starting off at 1.0 here. Then they're going 2, 3, 4, 5. 2, 3. I know it goes up higher. That's as far as the plot goes. Okay, then we have here, this is 0 on this one, and this is 1 over T. Right. So, and that's K to the minus 1. Kelvin to the minus 1. There are 2 different Ks. And then we have 0 to 0.1, and this is that equal 0.2. Okay, so if we draw a straight line from 3.2, that's our graph. We plotted the Ks determined at different temperatures, right? So if we go to the useful information, it should be here. The straight line expression that we're going to use is, yes, it's in the middle on the bottom. So we're looking at log K, and that's equilibrium constant, is equal to negative delta H over R times 1 over T. So there's Y, and there's X. There's slope M. And then the delta S, this is 0 also, over R. Okay. So that's our straight line plot. I don't know if this one has a name. I didn't give it a name, did I? A lot of these plots are named after people that proposed them. Okay, so what's the question? Go back to the question. 42. Question is, which of the following is consistent with this information? Oh no, wrong one. Right? Yeah, wrong one. I need to scroll down. to 52. Okay. There we go. What is delta S0 for the reaction in joules per mole K? So we're looking for this one. That means y-intercept is 3. And that's equal to delta S0 over R. So we know what R is, 8.3145. So we just say this one, this value times 3. And that should be about 25, 26, something like that. Yeah, C, 25. So delta S 0 equals 25. Yeah, that's right. 3 times 8 is 24, and a third of 3 is 1. So 24 plus 1 is 25. Using estimation powers. Okay. So if we wanted to know K, we would need to know the slope of that line, right? So how would we find the slope? Just in case I get tricky and change conditions. What's the slope of this line? Rise over run, right? So rise is over this distance, rise is 2 units, right? Negative 2, because it's going to rise is negative 2. And then run is 0.2. Right, so it's a negative, the slope is a negative 10. Is that right? You just increase this one by 10. 20 divided by 2 is 10. That's it. Okay, so then we would take this and set that equal to this, because the negative slope is the negative values here. So you could either say this one equals negative delta H 0 over R, or you could just say this one's equal to that and just drop the negatives altogether. And then we know what R is, just say the R times this one would give you delta H. Right? So 8.315 actually be 83.1 would be equal to delta H. I mean, that's not close. E is close, it's just wrong power of 10. So you can get and if you wanted to do K, right, calculate K, you just plug in the value of the slope, the y-intercept, and the temperature, because the temperature is going to change the K. So you need whatever the temperature is, take the inverse, and you can calculate K at that temperature. Probably should have done one of those examples too. Okay, that was 256. Okay. All right. So we're in the same theme as the one we just left. This with me. 56. The equilibrium constant Kp in atmospheres for the dissociation reaction Cl2 has to be a gas if we're using K sub P. We're using partial pressure, so that has to be a gas. And it makes these 2 atoms. Was measured as a function of temperature in K. A graph of Kp, log Kp versus 1 over T for this reaction gives a straight line with a slope of minus 1.651 times 10 to the 4th. Okay, and an intercept 14.51. So we go back to our equation. Let's put it up here. Log K equals negative. Pardon me while I keep. Minus delta H0 over R 1 over T plus delta S0 over R. Yep. Okay, so this one, well, what's the question? The value of delta H for this dissociation reaction. Delta H. All right, so all we need is the slope. Right? The slope is equal to minus delta H0 over R. Right. Okay, so let's just substitute for R here. 8.3145. So 8.3145 times that value should give us the answer. Because the negatives go out. This one times that one. 8.3145 and 1.651 exponent 4 times. And that's equal to 1.37 times 10 to the 5th. And this value is in joules, right? So this is joules, and the answer is probably in kilojoules. Yeah, kilojoules. So we just take that much of this one and put it right here as a K, and it's 1.37 times 10 to the 2nd power kilojoules. Oh, standard notation. So move it two places, 137 kilojoules. There you go. Okay. Sound like somebody dropped off and came back on. Let's see if I'm right. Emma's still here. Here's Mary, Emma. Oh, Kyle's zooming in. Kyle, you better show up because I saw your car in the parking lot. I don't know if you heard me or not. 57. Let's scroll down a little bit and get 57. Okay. For a certain process at 300 K, so we just put the information we have up here, whether we need it or not. 300 K, delta G for this process is minus 12.2 kilojoules, and delta H is minus 7.0 kilojoules. If the process is carried out so that no useful work is performed, delta G is this means that it's spontaneous. Okay. And W, the amount of W max, the maximum amount of work you can get out of it is minus 12.2 kilojoules. Right, that's what this means. This doesn't matter. You know, I think that I've got the wrong answer there. E is the maximum amount of work that you can get out of the process. Let me check the wording again. Maybe there's a key to the wording. If the process is carried out, so no useful, it is, it's trick wording. if the process is carried out so that no useful work is performed, delta G is still minus 12.2. Just because we didn't get any work out of it doesn't change this value. Okay, it's a trick. The actual amount of work is equal to 0. But the maximum amount of work and the delta G are still minus 12.2. Yeah, that's a trick question. It almost caught me. Oh, and that's the last one. Last one that I picked out.